Section 5.5 talks about alternating series test. Actually, it talks about two different tests. Well, the first, not two different, one test, but another type of convergence or divergence. Alternating series is a series that switches signs from positive to negative, specifically, or from negative to positive. It doesn't matter which order that runs in, but it has to be alternating each term. If you have two terms that are positive and two terms that's negative, that wouldn't be an alternating series. It must be consistent, positive, negative, negative, positive. So here, either the first term, assuming that B, oops, that didn't work. Assuming that B sub n for any n is bigger than 0, it's positive. So if this is positive, then this term is positive, negative, positive, negative. Or you start with a negative, then a positive, then a negative, then a positive. That's called alternating. So first condition, B sub n must be positive. 2, if the limit as n approaches infinity, oh, it must be decreasing. I forgot about that. That's what this is saying. If you take any term, it should be bigger than the previous term. So let's go the other way around. It sounds complicated the way I said it. Let's read it properly. To take any term, it should be smaller than the previous term. So it's decreasing. So 1, it's positive. 2, it is decreasing. And the third condition, the limit as n approaches infinity of B sub n equals 0. If that's the case, remember, if the limit of the sequence part equals 0, that doesn't mean anything for any other series, then it is alternating. If it's alternating and the limit equals 0, automatically it converges by the alternating series test. That's how it works. Otherwise, it diverges. So, I have a series that's alternating. I look at the term that's not alternating. If that is positive, number 1. 2, it's decreasing. 3, the limit of that sequence part is 0. Then we say the series is converging by the alternating series test. So that's what the test is all about. Now, we're going to be dealing with this idea of absolute convergence or conditional convergence. And note, given a series, if the series of the absolute value converge, then the series of the original converge. It's very hard for an absolute value to converge. Now, let's talk about what it means to be absolutely convergent. A series is absolutely convergent if the series of the absolute value of n converge. If that converge, then we say the series of A sub n is absolutely convergent. So given a series, slap an absolute value on it. If that converge, then we say this series is absolutely convergent. We're done. This is the tricky piece. Conditional convergence. Conditional convergence happens when the series itself converge. When you slap an absolute value on it, it diverges. So, if I test a series and I know it converge, then I should aim for absolute value first because I have to do that anyways. Now, if the original series diverge, you're done. There's nothing to it. But if the original converge, then you have to test the absolute value and see how that plays. Let's start. Problem number 1. I'm glancing at this. I already know that the limit as n approaches infinity of n over n plus 3 is infinity over infinity. By L'Hopital, the limit as n approaches infinity of 1 over 1, which doesn't equal 0. Therefore, it diverges by divergence test. Done deal. Nothing to it. Here we're checking whether the series is convergent absolutely or conditionally, or not at all. Not at all in this case. It diverge. Now, of course, you could say, but wait a minute, this limit is not 1. That's alternating. That limit is 1 or -1. Well, it means it doesn't exist. That's still not equal to 0. It doesn't matter. So it's sufficient to show the limit doesn't exist, and you're done. Here is another series. I'm glancing at this series, and I'm thinking, and I'll give you an example in a minute. So think of this way. If I'm looking at the series of 1 over n, we all know that diverge. That's harmonic, p equal 1, whatever you want to call it. Watch what happens if I slap a -1 to the n on it. Now I could say 1 over n is positive. It is decreasing. The limit as n approaches infinity of 1 over n equals 0. Therefore, it converges by alternating series test. So most of the all of the p series, divergent p series converge if you make them alternating. Notice if you put an absolute value on this, it becomes that. So even though this initial converge, but the absolute value diverge, this is what's known as conditional convergence. So putting an absolute value on a series, it becomes harder to converge. Glancing at this problem, well, this is positive. It is decreasing because n only appears in the denominator. The limit as n approaches infinity of 1 over square root of n plus 3 equals 0. Therefore, converge by alternating series test. Well, what happened if I'm going to test for absolute or conditional? So the series converge. I'm right there. Now I need to check. If this diverge, it's conditional convergence. If that converge, it's absolutely convergent. So I suggest you start with the absolute value first and then work your way, but whatever works. Now, if I put an absolute value on it, all what the absolute value does, it eliminates the alternating part. So the limit as n approaches infinity equals 0 is no longer useful. Now, this is dominated by 1 over radical n. That's a series p equal 1/2, right? N to the 1/2 less than 1. Therefore, it diverge. I take the limit as n approaches infinity of 1 over radical n plus 3 divided by 1 over radical n. That is the limit as n approaches infinity. If I divide by the highest power term of the denominator, therefore, they both diverge by limit comparison test. Therefore, this is a conditionally convergent series. The original converge and the absolute value diverge. That's the definition of conditionally convergent. Well, here's another one. Looking at this problem, well, I'm aware what this looked like. I'm going to take the limit as n approaches infinity, and I'm going to split that up, n over n minus 1 over n to the n. Limit as n approaches infinity of 1 minus 1 over n to the n. That's 1 to the infinity. That is e to the limit as n approaches infinity of natural log of 1 minus 1 over n to the n. Again, L'Hopital's rule, remember that section. And that's going to be n natural log of 1 minus, that's infinity times 0. So that is e to the limit as n approaches infinity, and that's natural log 1 minus 1 over n divided by 1 over n. And now I would say as n approaches infinity, that's 0 over 0. By L'Hopital rule, that's e to the limit as n approaches infinity. 1 over 1 minus 1 over n times 1 over n squared divided by negative 1 over n squared. Those cancel out. That approaches 0. That is e to the negative 1, which doesn't equal 0. Therefore, diverge by divergence test. And that's all there is to it. So if the original series diverge, you're done. No need to really make it harder than it is. Done deal. Okay, how about this problem? Well, first things first. if I take the limit as n approaches infinity of the sine squared of n, that does not exist because of oscillation. It's gonna be bounded between 0 and 1 back and forth. Therefore, diverge by divergence test. Again, if the original diverge, you're done. There's nothing to do. So you could just say doesn't equal 0. All good. That's what you have to show to quote the divergence test. Now, I'm looking at the following problem. Well, if I take the limit as n approaches infinity, okay, that's working. So 1, this is positive. The decreasing part, we know it's decreasing because you're looking at the sine of 1 over n, the sine of 1 radian, the sine of 1/2, the sine of 1/3, sine of 1/4. It's getting closer and closer to 0. Limit as n approaches infinity of the sine squared of 1 over n that approaches 0. That is the sine squared of 0, which is 0. Therefore, converge by alternating series test. Done deal. Now, if I look at the series n equal 1 to infinity of the sine of 1 over n squared, the absolute value will eliminate that part. I'm going to combine that with the angle squared. This is a p series. And if I take the limit, and why did I take that? Well, because I know how that plays. The limit as n approaches infinity of the sine of 1 over n squared divided by 1 over n squared. Limit as n approaches infinity of the sine of 1 over n over 1 over n squared. We know that's a 1. You could use L'Hopital if you wish, but we know that's a 1. We memorized that from the first semester, bigger than 1. Therefore, they both converge by limit comparison test. And what's our conclusion? If the absolute value converge, we conclude that this series is absolutely convergent, which is why I was saying if I was you, I would start with the absolute value first. Unless I see the limit is not going to be 0, and then I go from there and take a shortcut. And if I'm looking at this series right here, well, oh, that's simple. If I take the limit as n approaches infinity, natural log of 1 over n, that's going to approach 0. Recall how if you are approaching 0, that's log is going to approach negative infinity, which doesn't equal 0. Therefore, diverge by divergence test. And again, if the original diverge, you're pretty much done. This problem, as is, I'm going to say this is positive. Decreasing, well, not so fast. I'm going to take a derivative. That is 2x times 1 plus x to the 4th minus x squared times 4x cubed divided by 1 plus x to the 4th squared. I'm going to factor an x out of those. That's 2 plus 2x to the 4th minus, take an x out of that, 4x to the 4th divided by 1 plus x to the 4th squared. That is x into 2 minus 2x to the 4th, 1 plus x to the 4th squared. Where does the derivative equal 0? That's when x equals 0. And plus or minus 1, we don't worry about this or this. We just pick a point to the right of 1. If I pick 2, that is positive. The denominator is always positive. But if I put a 2 there, 2 to the 4th, that's 1632. 2 minus 32 is negative. If the derivative is negative, the function is decreasing. So we could say decreasing, no problem. And 3 or 2, the limit as n approaches infinity of, if I divide by the highest power term of the denominator, I'm in good shape. Limit as n approach, of course you could use L'Hopital twice. 1 over n to the fourth plus 1, 1 over n squared. That is 0, that is 0. That's 0 over 1, which is 0. Therefore, converge by alternating series test. All right, let's look at the next problem. Well, again, if we take the limit as n approaches infinity of 2 to the 1 over n, that is 0. 2 to the 0 is 1, which doesn't equal 0. Therefore, it diverges by divergence test. Oh, I forgot to check if this was conditionally convergent or not. Okay, sorry about that. Let's just shift this entire problem to the right since it's so short. A good thing I did that first, otherwise I was going to squeeze a lot of. Okay, here we go. So that is that. Okay, so if I was to take the series of n squared over 1 plus n squared to the fourth, I could say, look, this 1 plus n to the fourth and n to the fourth, this is bigger. So 1 over is smaller, multiplied by n squared. This is the series of 1 over n squared. P equal 2 bigger than 1, therefore converge. Therefore, the series n equal 1 to infinity of n squared over 1 plus n to the fourth converge by comparison test. Therefore, this series is absolutely convergent. If I was to do this first, I would have saved myself all of this work, because if it's absolutely convergent, no need to check if it converges, it automatically converges. So this problem, in case you don't know what that is, when n equal 1, we start at 1, that's negative 1 over 1, cosine of pi. When n equal 2, that's a 1 over 2. N equal 3, 3 pi, 4 pi. So this is nothing more than the series n equal 1 to infinity of negative 1 to the n over n. The alternating part, every time you have alternating, that's negative 1 to the n power. And we notice 1, 2, 3, 4, that's arithmetic. You could figure that one out if you need to. But there it is. So what do we know? 1 over n is positive. It is decreasing. And the limit as n approaches infinity of 1 over n equals 0. Therefore, converge by alternating series test. Very good. If I slap an absolute value on it, all what the absolute value does is take away the negative. We say, look at that, p equal 1, therefore it diverges. Out of both of those conditions combined, we know that this is conditionally convergent. And if we look at this, the same deal happens. If I want to look at that, this is n equal 1, that is 1 over 1 times 1. If I put 2, 1 over 2, sine of pi is 0. If I put 3, 1 over 3, sine of 3 pi over 2 is negative 1. 1 over 4, sine of 2 pi is 0. 1 over 5, the list goes on. So this is nothing more than 1 minus 1/3 plus 1/5 minus 1 over 7. So this is the series n equal 1 to infinity of negative 1 to the n again. Oh, I didn't check if this works. If you let n equal 1, the first one is negative. Good, it works. And this is 1, 3, 5, 7. That is arithmetic. A sub n is a sub 1 plus n minus 1 times the common difference, or simply 2n plus 1, whatever you like. 2n minus 2. So 2n minus 1 or plus 1 will do the trick. Okay, and there it is. Well, what do we know? This is positive. It is decreasing and only appears in the denominator, and the limit as n approaches infinity of 1 over 2n minus 1 equals 0. Therefore, converge by alternating series test. And if I was to look at the absolute value, that will be the series n equal 1 to infinity of 1 over 2n minus 1. This is dominated by 1 over 2n, so 1/2 the series of 1 over n, p equal 1, diverge, limit as n approaches infinity of 1 over 2n minus 1 over 1 over 2n is the limit as n approaches infinity of 2n over 2n minus 1 by L'Hopital, because that's infinity over infinity. That is the limit as n approaches infinity of 2 over 2, which is 1 bigger than 0. Therefore, they both diverge by limit comparison test. And from those two conditions combined, we know that therefore it's conditionally convergent. So condition convergent is the most work. Now let's talk about, let me see if I need another video. No, that's it. So let's talk about this. This is, again, they talk about error and they give this formula that we don't need. I'm putting in integers. Remember, those numbers are always small numbers. But let's talk about integers. If I'm adding those, do you agree if I add those three and stop there? In absolute value, this is bigger than this sum's going to be, because in absolute value, if they're alternating, the next term is going to have an opposite sign, and I'm going to end up subtracting, and that's going to shrink down drastically. And if I was to add those, say, look, this is the sum right there, and I'm going to stop right there. There's the remainder. Do you agree in absolute value 6 is larger than the rest? Because 6 in absolute value, if it's positive, the next term is negative. You're going to subtract, and it's going to get a lot smaller. And if it's negative, the next term is positive, and you're going to subtract, and it's going to get a lot smaller. So if I'm adding terms and I stop, in absolute value, this will be bigger than the rest of the sum, because that's decreasing, and you're picking a big term and you're no longer adding or subtracting to it. Keep that in mind. Here we are. We're talking about the following. Use estimate to evaluate the value of n that guarantees that the sum of the first n terms in the alternating series differs from the infinite sum by at most the given error in this case. Okay, don't worry about all the symbols and all of that. So basically what we're saying, look, we're going to take the sum n equal 1 to infinity negative 1 to the n plus 1 times 1 over n. And let me list a few terms out. That is 1 minus 1/2 plus 1 over 3 minus 1 over 4 plus 1 over minus 1 plus 1 over 7 minus 1 over 8. And the list goes on. Now notice what they want. They want the error to be less than 1 over 100. That is 0.00001. Well, this is 0.1. Do you see how far we are? So what I have to do, I have to add ... let me see. I need 1 over 100,000. And 1 over 100,000, that means I put in 100,000. 100,001, that's negative. The term before it is a positive 1 over 99,999 plus 1 over 100,001. If this is the error that I want, and this term is that, all what I have to do is to figure out the actual error in my estimate. In absolute value, it's the term after that, whether it's positive or negative. And that's pretty good. What does that mean? They're saying, look, we want the error not to affect the 5th decimal. So figure out where the 5th decimal is and stop right there. Now, instead of taking those infinite terms, this term is bigger than the next one, because the next one is going to subtract off of it, and that's going to make it a lot smaller. And let me show you again. If we're looking at this series, we're looking at a series n equal 1 to infinity negative 1 to the n plus 1 over radical n. This is 1 over 1 positive minus 1 over radical 2 plus 1 over radical 3 minus 1 over radical 4. Now let's see. They want the error to be less than 1 over 1,000, which is 0.001. Well, if this list goes on, to get 1 over 1,000, I must substitute 1 over 10 to the 6. 10 to the 6 is 0.001 because the square root of that is 10 cubed. Now, is it positive or negative? If you put in 1,000, that's going to be negative. So the next term is 1 over the square root of 10 to the 6, that's 1,000,001. So if I stop there, I am aware that the maximum error will be less than or equal to 1 over the square root of 100,000,001. And that's pretty much how we're going to play this. And that's all there is for this section.